Yo, what's going on guys? Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And today finally we are starting off with our very first non-linear data structure, which is tree data structure. So this is just an introduction and it's a very important video because this is where we start off with the non-linear type of data structures, and don't worry, we'll take a differentiation between linear and non-linear data structures in a separate video. But this is just an introduction to the tree data structure, which is a non-linear data structure. This video is very important guys, and the topics that we are going to cover in this video is as shown on the screen. First we'll start off with what is a tree data structure. We'll try to understand how a tree data structure looks by taking a real world example and then comparing it with our data structure example. We'll also see what is a binary tree. We will also understand some important tree terms and some important tree properties. Those are absolute important. Those are fundamentals which you need to know. We will see the logical diagram in the terms of implementation of how it would look like when we actually implement a tree data structure programmatically. And then at the end we will simply list down some of the types of trees, some of the variations, as well as the applications of tree data structure. Please make sure you watch this video till the end. This is a very important data structure. It has a wide range of applications, many variations, and it is one of the most widely used data structure in real world applications also. So with that being said, let's get started. If you're new to my channel, my name is Tanmay Sakpal and I do a lot of computer science and information technology video tutorials like computer programming, development, technology talks, and a lot more on this channel. So if that's something you're interested into, then definitely subscribe and turn on the notifications to get the latest updates and never miss out on such important topics. Now before we jump to the tree definition and understand the tree data structure, a quick recap. You can skip this, but we've already seen this in this DSA course, in this DSA playlist, and we know what is a data structure, right? If you've seen this DSA course, we already know what is data structure. Data structure is simply a way of storing and organizing data in the memory in such a way that access, management and modification becomes efficient. So it's nothing but how you store the data, right? Now why am I taking a recap? It is because which data structure to use depends upon many different criteria. Some of them I've listed as follows, which is what type of data needs to be stored. The next is the cost of operations like read, write, update, depending upon which is more efficient. So for some applications, maybe a queue data structure is much more efficient than compared to a stack, or a linked list is much more efficient compared to an array. We've already seen a differentiation between array and linked list in the previous tutorial, and we've seen which one is better in what scenarios. So same on those lines, another criteria is memory usage and efficiency. Then we have ease of implementation, and lastly we have maintainability. And of course there are many other criterias, but the point being said over here is every data structure has its own pros and cons with its own unique properties and some drawbacks. So it depends upon the application, depends upon the condition on which we decide which data structure is supposed to be used. So I just wanted to give you this recap. So now that you've understood what is a data structure, which you already had, but this was just a recap. So far in this entire tutorial course, as I mentioned, we've covered quite a lot of linear data structures. And to give you a basic explanation of what is linear and non-linear, in a linear data structure, data is arranged in a sequential manner. So we have a logical start, we have a logical end, and every element has a next element and a previous element. So if you see on the screen, I have denoted the four basic linear data structures which we already covered: arrays, stack, queue and linked list. If you observe array, you can see data is arranged in a sequence, in a proper sequential order, in a linear order. In a queue also you can see we have data coming in from one end and going out from the other. So we have a rear and a front, that is a logical start and end. In a stack also, data is pushed in this direction and popped out from the same end, but it is still arranged in a linear way, in a sequential way. And linked list, again you can see we have every node arranged one after each other. So all of these data structures are linear in a sense that the data is arranged in a sequential manner. So now that you've got a brief idea about linear data structures, let's see what is a tree data structure. So the definition of a tree data structure is: a tree is a non-linear data structure that simulates a hierarchical tree structure with a root value and subtrees of children with parent node represented as a set of linked nodes. Okay, so before we understand the technical aspect, Let's take a real world example of what is a hierarchical tree. So let's take an example of a typical college hierarchy, So in a college we have a chairman, we would have a director. So a director is under the chairman. Then under the director we have multiple HODs, that is head of departments. So let's say in a college we have multiple departments. So we have the science, we have commerce, and we have arts department. So we have their individual HODs. They all report to the director. Under the HOD we have senior faculty 1 and 2. Over here we have only one senior faculty, and over here we have 3 senior faculties. And the hierarchy would go on. We would have some junior faculties under the senior faculties and so on. So this is a real world example of what a hierarchical tree would look like. There are many other examples. In fact, you have your own family tree. You have a hierarchy in a company, in an organization, and you have many different types of hierarchical data in real world. So a tree data structure is a data structure that simulates this behavior. Okay. So in data structures now, coming into the data structure side, our data structure is gonna try to simulate this same hierarchical behavior. When I say that, it would mean that the data is gonna be organized in a hierarchical tree kind of scenario. So let's see how that looks, and then we will again go through this definition. Okay, so on the right hand side, this is where a logical tree diagram would look like for a non-linear data structure of a tree. So again, let's go through the definition now. So a tree is a non-linear data structure, and the reason why it is non-linear is because data is not organized in a linear way. You can see over here, you have multiple links starting from one node. So these blue circles are what is called as nodes. Okay. And we'll talk about that as we move ahead. But you can clearly see that it is not linear. So this tree is a non-linear data structure that simulates a hierarchical tree structure. So this looks pretty much like this with a root value. So the top node is going to be called as the root node. So this is root, which is at the top. If you see in the real world example, the chairman would be the root. Then we have and subtrees of children. So this root node is pointing to two child nodes, that is 2 nodes below it. Let's name these nodes. I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So I've just named them randomly. Okay, this is not like there is a way to name them. This is just for our reference for now. And you can see root node is root node number 1. After that, it has 2 nodes right below it, which is node 2 and node 3. So these can be individually considered as subtrees of children. So for 1, the children's are node 2 and 3. So if you only see everything below 2, it can be also called as a tree only, right? So it is a subtree. Similarly, this is also a tree data structure itself. So these are subtrees with a parent node being root node over here, and it is represented as a set of linked nodes. So these yellow arrows are nothing but links, or they are also called as edges. Okay, so they are linked in a way that they look like a tree diagram. Now remember, in a linked list also we had nodes, but they were linked in a sequential way. Over here in a tree we would have nodes, but the linking would be done in a way that they represent a hierarchical tree. Okay, alright. So now that a little bit of basics is covered, a little bit of definition is understood, let's try to get into more details about some important terms of tree data structure. Okay, so on the left hand side we have some important tree terms. Let's go one by one. If you're making notes, you can take a screenshot, you can note them down, but don't worry, I'm going to be sharing all this theory along with the diagrams on our official website. So you can just copy paste it and prepare your notes for your exams. There's a link in the video description to our official website for this article. Just go there and you can refer these notes later on. But now let's go one by one through all these different tree terms. So point number 1, root. The root is a special node in a tree, and the entire tree is referenced through it, and it does not have a parent. So that would be the top node, which is node number 1, and it is called as root node. So it's a special node because there is only one root node and the entire tree is referenced through it. So you can go to any node starting from the root node. Also, it does not have anything above it, so there is no parent of this root node. So obviously the next question is, what is a parent node? So that is point number 2, and parent node is a node which is an immediate predecessor of a node. Predecessor means the node that comes before it. So for node 2 and 3, which node comes before it, immediately it is root node, which is node 1. So for node 2 and node 3, 1 is their parent, which basically makes 2 and 3 as child of node 1. So that is point number 3, child node. Child node is all immediate successors of a node are its children. So after node 1 is directly linking to node 3 and node 2. Hence 2 and 3 can be considered as children of node 1. I hope I'm making sense over here. Please do note these points. Do note these terms. These are absolutely important. In further tutorials, in further videos, we will constantly refer to these terms directly. And I'm gonna assume that you already know. So hence, please pay attention. Now moving on, we have the concept and the term of siblings. Nodes with the same parent are called siblings. So over here, if you see, node 2 and 3 have the same parent as node 1. So they can be considered as siblings. If you see below, let's go one level down. Node 2 is the parent of node 4, node 5 and node 6 because it is immediately predecessor of the node. That is, node 2 is directly linked to node 4, node 5 and node 6. So this makes node 4 and 5 and 5 and 6 and 4 and 6, all of these 3 as siblings, as well as all of them as child node of node 2. Okay. If you go one level below, again, node 9 and 10 are siblings because their immediate predecessor is node 5, which is their parent, which makes 9 and 10 as children of 5. Make sense? Alright. So siblings is done. Let's move down. We have point number 5, which is leaf. So leaf is the last node in the tree and there is no node after this node. So at the bottom is where we will find the leaf nodes. So over here that would be node 9, node 10, node 11, and also at this level we have node 8 because all these nodes do not have any node below it. So is 9 linked or is 9 pointing to any other node? No. Is 10 pointing to any other node? No. Is 11 pointing to any node? No. And 8 is also not pointing to any node, which makes them leaf nodes. Alright? Okay. Let's see point number 6. Point number 6 is edge. Edge is the connection between one node to another. It is the line between two nodes or a node and a leaf. So this yellow line is what I'm trying to say is an edge. It is also known as a link. So it can be link and edge. Please remember both these two terms. It is just the line that is connecting between the two nodes. Now do note that these lines are not bidirectional. They only go in one direction, which means that you can go from node 1 to 3, but you cannot come back. This is not valid. So when you actually implement a tree data structure, the traversal of nodes will only start from root node and it will go to the child nodes and it will go below only and not in reverse order. Okay. So hence the arrow is also in one direction. It is not like this. So keep in mind that the edges and the links are not bidirectional. They are only in one direction, and that is the downward direction. The next term is the path. So path is a number of successive edges from source node to the destination node. So if the destination node is 7, and I just mentioned that we will start from the root node only, the path would be this edge and then this edge, right? So this is going to be our path. Another example, if this is the destination where we want to reach, we will have to traverse from 1 to 2, we will have to traverse from 2 to 5, and then we will have to traverse from 5 to 10. So 3 edges come between root node 1 and the destination node, which is a leaf node of 10, and that is the path. The 8th term over here is the degree of the node. So what is degree of the node? So degree of a node is equal to the number of children a node have. So if you try to calculate the degree of the root node, you simply count the direct children it has. So we have node 2 and node 3 as children of node 1. So degree will be equal to 2. It's simply the number of children one particular node has. So if you go and calculate the degree of node 2, 2 has 3 children, which is 4, 5 and 6. So here the degree is going to be 3. Also degree of the tree is also one term, which is the maximum number of children one particular node has. And in this logical tree diagram, the maximum children any node has is 3, which is node n2 or node 2, which has the maximum number of children, which is 3. So the degree of the tree you can say is also 3. Okay. Okay, so these were some important tree terms. I hope they were easy to understand. let's see a few properties of tree data structure. Okay, so property number 1 says that a tree can be termed as a recursive data structure. So what does this mean? Now I'm assuming you already know what is recursive behavior or recursion or recursive function. Recursion basically means that repetition of same entity or same activity over and over again till a particular condition is met. Okay, so a tree can be considered as a recursive data structure. So what does this mean? So if you start from root node 1, this whole data structure is a tree. Now if you go to its child nodes and divide it into two subtrees, that is, this is subtree 1 and this as subtree 2, you can safely say that even these two are tree data structures. Now you can again further divide these subtrees into smaller subtrees and you can keep on going till you ultimately reach a single node. So this is the recursive behavior of this tree data structure, which means that you can divide up entire tree data structure into smaller subtrees over and over repetitively till you reach a single unit, that is the node of the tree. Okay, hence this tree can be termed as a recursive data structure. So this recursive property is something that we will use in the implementation side also. And as I mentioned, recursive in this context simply means that a tree data structure can be divided into smaller subtree data structures recursively till you reach a single entity, that is the node. Okay, let's move forward. Point number 2. So in a valid tree, for n nodes, we have n minus 1 edges, that is links. So if you calculate the number of nodes over here, we have 11 nodes. Let's calculate the number of links. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. You can see we have 11 nodes. So 11 minus 1 is 10. So that is the number of links. So if n is equal to 11, the number of edges is going to be 11 minus 1, which is equal to 10. So this is always going to be true for a valid tree. When I say valid tree, it means that it is a proper tree data structure and not something other than a tree data structure. This property only applies to a valid tree data structure. So if you simply have one more edge to one more node, let's say this is node 12. So this would be edge number 11 and node will become 12. So number of nodes again will become 12 and edges will become 11. So again the same property is followed. Okay. Alright. Now let's see 3 important properties, or you can say these are important attributes of a tree. The first one is depth of node. So depth of node represents the number of edges from the tree's root node to that particular node. So whenever you want to calculate depth of any node, you calculate the number of edges from the root node to that node. So if I were to calculate depth for this node 6, I simply have to calculate the number of edges from this root node. So this is the root node till this node 6. So we have this one first link which goes from 1 to 2. Then we have this second link which goes to our node 6. So the depth for node 6 is equal to these two edges. So that is 2. Okay. Let's calculate depth for this node. So depth for node 9 is going to be equal to this first edge. Then we will go from 2 to 5. This is the second edge. And then we will go from 5 to 9, which is our destination. So this is the third edge. So the depth over here is 3. Okay. Basic enough. One thing to note that is the depth of root node is always going to be 0 because there is no node above root node. So the depth of root node is always going to be 0. Okay. Keep that in mind. It can be asked in your exams or as a trick question. Moving forward, what is height of the node? So height of a node is the number of edges. Again, it is number of edges only, but it is different than depth of node. So height of node is the number of edges on the longest path between that node and a leaf. So when you calculate depth, you start from root to the particular node. But when you calculate height, you start from that node and take the longest part till you reach a leaf. Okay. So let's see what that means. Let's calculate the height of node 3. So let me write over here. Height of node 3 is equal to the number of edges on the longest path between that node and a leaf. So for node 3, if you go from 3 to 8, this 8 is also a leaf. We have one edge. But for 3, we can go in this direction also. We will go from 3 to 7, which is one edge. And then we can go from 7 to 11, which is second edge. And this is also a leaf node. So we have two options of leaf nodes starting from node 3. We have to select the longest path. Which is the longest path? Obviously, we will go from 3 to 7 and 7 to 11 because there are two edges. So 2 is greater than 1. So height is going to be 2. Okay. So height of node 3 is going to be 2. Let's calculate the height of node 2, which is this node. So we have first path going from node 2 to 4, and 4 is also a leaf node. We have one path going from 2 to 5 and 5 to 9. So one edge and second edge. Again, we can also go from 2 to 5 and 5 to 10. Again, one edge and second edge. And both 9 and 10 are leaf nodes. And last direction which we can go is from 2 to 6. 6 is also a leaf node, so this is 1. So obviously, the longest path is comprising of two edges. So height of node 2 is 2. Lastly, height of root node can be considered as this path, that is 1 to 2, 2 to 5 and 5 to 10. You can also go from 1 to 3, 3 to 7 and 7 to 11. In both ways, we have height of root node, which is 1, is going to be equal to 3, which is going to be the longest path. So I hope you've got how to calculate height of node and depth of node. A lot of times students get confused between depth and height. It can be different. So please note these points down and how to calculate them very properly. And last property is height of tree. And the height of tree is always equal to the height of root node. So height of 1, which is this root node, is equal to 3, which is also equal to height of tree. Okay? Alright. So these were some important tree terms and properties. And now let's move forward. So far what we've understood is what is a tree data structure. We saw the definition. We saw the comparison of a real world tree hierarchy and also our logical tree. But so far what we've seen is a very general tree. When I say general, it is not a variation or a special type of tree. Now we'll see what is a special type of tree, which is called as a binary tree. And as the name suggests, a binary tree is nothing but a tree where each node or where every node can have maximum of 2 childs. Okay? So that is the only specific definition for a binary tree compared to a general tree. That is, in a binary tree, every node can have only maximum of 2 children. So over here you can see node 2 has 3 children. So that is not valid in a binary tree. So let's remove out one node and let's see how a binary tree would look like. Okay, so now if you can see, we've removed one child of node 2 and now every node in the binary tree has maximum of 2 children. So you can see this is the root node, it has 2 children, which is 2 and 3. 2 also has 2 children, 4 and 6. 3 has maximum 2 children, 7 and 8. And 7 has one child, which is also valid in a binary tree. The rule is that you cannot have more than 2 child per parent. Okay? Now the reason why we are trying to understand what is a binary tree is because majority of the future tutorials are gonna involve some form of binary tree. Of course, we will take a look at different types other than binary tree as well. But a lot of work is gonna be done on binary tree. Hence, this is the initial introduction to what is a binary tree. And now that you've understood what is a binary tree in a very general way, let's take the same binary tree in the form of an implementation diagram, in the form of a little bit of programmatic way. How would it look like when you actually implement this tree data structure, this binary tree data structure in the form of code? So on the left hand side, you can see binary tree diagram in the implementation view. That is when you write some line of code to create these individual nodes and to try to link them. So over here, each of this circular node programmatically would look something like this. Now if you've seen the video tutorials on linked list, this would be a little similar. A node typically would comprise of a left pointer and a right pointer. When I say pointer, a pointer is nothing but an entity in a node that points to the child node. Okay? For C and C++, they would be actual pointers. But if you're using some other general purpose programming language, it would be some reference or some other mechanism which would point to the next node. The center part would be the data part where the actual value would be stored. So this same binary tree is converted into an implementation view. So the first node N1, this is the name of the node N1, is the root node. This #10 is the actual address where the node would be created in the memory when you write a program. So this is nothing but the address. Of course, it is a fictitious address. It is not a real address. Real addresses look different. We have just taken this for our representation. Okay. So N1 would be a node created in the address of #10 in the memory. Let's say it has some value of, let's say it is 50. So this 50 is an integer value. So this data would be of type int. Of course, it can be anything, but for simplicity purpose, we've taken int. Then we have N2 and N3 created at address locations #23 and #27. Now, in a binary tree, we have a left child and a right child. So the child which is left of the tree obviously is known as the left child, and the one that we have on the right side is known as the right child. This is pretty basic. Now N1 would point to both left child, I'll represent it as LC, and right child as RC. So N3's address #27 should be stored in the right pointer. So you can see star left and star right means these are pointers of type node itself. So they would point to N3 for the right child, and #23 is the address of N2 for the left child. Let's say they have some individual values of 7 and 1. Similarly, N2 for the left child would have the address of N4. N4 is created at address location #73. So 73 is stored over here. Let's say it has the value of 2. For N4 being the leaf node, which means that it does not have any node below it, the address stored would be null, right? For the left child and right child initially, whenever you add another node under it, that address will be stored over here. But since it is a leaf node, the addresses inside the leaf nodes left and right pointers would be null. For N3 is pointing to N6 as left child, so #13 is stored. #71 is the address of N7, which is as the right child, RC, and this is left child. Let's say it has the value of 11 and 21. N6 has only a left child, which is N8. Let's say it has the value of 8, and it is at the address #55. Hence 55 is stored in the left pointer of N6, which is the parent of N8. And N5 has left and right as blank. Let's say it has the value of 5. Okay. Alright, so this is how the implementation view would look like when you actually create the node. I'll show the node class on the right, you can see on the screen. So this is a C++ code where you create a class node inside which you will have two pointers of the same type of node. So node star left and node star right. And then we have a data type which is of type int in this case. That can be anything. It can be a complex data type also. It can be float, it can be double, it can be character or whatnot. So this center value can be anything. It can be an alphabet, A, B, C, something like that. It can be another class. It can be a user defined class. You can create a person class and store those datas over here also. So that is completely upon the application. Also your node can have a unique identifier as key also. So one more value of key can be added over here. That's what we did in the linked list where key was supposed to be unique to every node. So if you want a binary tree to have duplicate data, you can keep an extra entity as key which is supposed to be unique so that you can uniquely identify every node. But that's something that you can do yourself according to your necessity. But in general, this is how a binary tree would look like in the implementation side. And I hope you've got a little bit of understanding of both the logical view as well as the implementation view. Okay, so now that you've understood in depth about tree data structure, at least at the theoretical side, a lot of terms, a lot of properties, the visual diagrams, let's come to the last part where we try to list down some types as well as the applications. Starting with types, we have many types of trees. We have general tree, which we just saw. We also saw binary tree. Then we have another variant in binary tree, which is binary search tree. We have AVL tree, spanning tree, B plus tree, heap. Heap is also of type of tree. And we have some more examples also. And this is the reason why tree data structure has so many variations and so many applications in real world scenarios. Because for every different type of application, there is some type of tree which is suitable for it. And that is the reason why tree data structure is absolutely important. And right now we've just listed the types of trees, but as we progress in this tutorial's course, we will try to understand each of these types individually in detail. But right now I've just listed them. So moving on to the application, tree data structure can store hierarchical data. We just saw that in the very beginning, because a tree data structure pretty much simulates a hierarchical tree. So it is best suited to store hierarchical data like folder structure, organization structure, any real world scenario where there is some kind of hierarchical data. Then point number 2 says binary search tree, which is a variation of binary tree, is a tree that allows fast search, fast insertion, fast deletion on sorted data. So this is where it is more efficient. A heap is a tree data structure which is implemented using arrays, and it is used to implement priority queues. Then we have B and B plus trees that are used to implement indexing in databases. So a lot of indexing in databases that happens is using these data structures. Trees are also used to store router tables in routers, routing data and whatnot. Then trees are also used by compilers to build a syntax tree. Trees are used to implement expression parsers and expression solvers. So these are some technical terms, but there are many more applications which I could have listed. You can simply Google them out and you'll realize that tree data structure is pretty much used in most of those real world applications, especially when there is a lot of complication involved. And hence it is very important that we understand tree data structure in detail. Okay, so I'm going to conclude this video over here. I know it got a little lengthy and pretty theoretical, but this was very important to get started with tree data structures, to understand the basics, to understand the fundamentals. As we move forward, as I mentioned, we will see the different types, we will see some implementation, we'll see the tree traversal, we'll also see some comparisons and whatnot. So I hope this video was understandable. I hope you've understood what is tree data structures, at least at the theoretical level and diagrammatic and implementation view. If you like this video, please give it a thumbs up. Let me know in the comments how this video was. Do share it with your friends. And I'll see you guys in the next video where we'll talk more about tree data structures. Thanks for watching. See you in the next one. Peace.